Hello everyone, my name is Clement Gehring, and today I'll be talking to you about our paper, Reinforcement Learning for Classical Planning, Viewing Heuristics as Dense Reward Generators. So heuristics can vary a lot in terms of how applicable they are and how general they are. And so at kind of the higher end of generality, we have domain-independent heuristics, such as some that come from relaxation, which can exploit the structure and how we define the problem and how we describe the domains. And then if you go into more specific, then you get domain-dependent heuristics that can leverage more structure in the domain, but unfortunately domain-dependent heuristics can be quite hard to find. But if you do, then you now have this usually better heuristic that you can apply to a wide range of problems within that same domain. And you can go one step further and then invest a lot of effort to find a problem-specific heuristic, which likely will be much better than any of the other heuristics. But unfortunately, it becomes very, very hard to kind of get back the computation or the effort required to come up with these heuristics, because then you can only solve this one problem. And so you might as well have spent that effort just to solve the problem to begin with. And so if you wanted to learn a heuristic, well, one way you could do this is through the use of value-based reinforcement learning, which can let you learn an optimal heuristic for either a problem-specific, or if you have the right representation or the right formulation, you could even do it for a domain-dependent heuristic. But unfortunately, RL requires many interactions and a lot of computation, which makes it often intractable for the kind of problems that we want to solve in planning. Our goal in this work is to combine RL with domain-independent heuristics to efficiently learn domain-dependent heuristics. And so our contributions can be broken down into two main points. The first is about how we represent these domain-dependent heuristics, and we do this through the use of neural logic machines, which allows us to learn a goal and problem conditioned function. And finally, the second part is how to make RL work, or how to make it all tractable. And so we make use of potential-based reward shaping to efficiently learn this domain-dependent heuristic, and it ends up being a correction to a domain-independent heuristic. And so we'll get into that in a bit. But first we'll talk about how exactly we can represent this domain-independent heuristic. And so simply just applying a neural network or a conventional feed-forward neural network won't work, because inherent in the formulation of these architectures is that the input size is always fixed, which makes it not really applicable to cases where we have varying number of objects and things like that, and we would like to be able to apply it to an unbounded number of objects. And so how we tackle this problem is we first encode the grounded state and goal predicates into a series of binary n-dimensional arrays grouped by arity, and then we feed this input to a fairly recent architecture called neural logic machines. And now I won't have time to get into the details of how these neural logic machines work, but at the high level you can think of them as a sort of soft first order logic formula that can be all differentiable and learned all at once. And so now that we have some way to encode this domain-dependent heuristic in a way that's differentiable, we can simply just apply nonlinear RL methods to it. We've got a specific set of choices that we've made that we detail in the paper, but this still doesn't address the problem that RL is slow, and RL is especially slow on problems where the rewards are sparse, which is the case when you're doing planning, because the reward is either 0 everywhere and 1 at the goal, or alternatively you could have -1 rewards or negative cost everywhere until you reach the goal. But in both cases, the reward doesn't really provide any information until you actually solve the problem, until you actually get to the goal. And so one way to get around that would be to add additional reward, and we call this reward shaping, and that's the solution that we consider. But there is a caveat, and something very important to keep in mind, is that if you carelessly shape your reward, you will most certainly change your problem in undesirable ways. And this is very much a case of careful what you wish for. But fortunately, it's been known in the RL literature for some time now that if you use something called potential-based reward shaping, you will be able to preserve kind of your optimality, or your problem, the form of your problem. And the way this is done is that you define a new reward function based on the old reward function, plus how this potential changes. And so this allows us to define a new problem that preserves the optimal policies, and so all optimal solutions are exactly optimal in both. And so it gives us a convenient way to inject prior knowledge. And so in this case, this is where we use the domain-independent heuristic as a potential to guide the agent towards the goal. Yeah, to guide the agent towards the goal. And but unfortunately, it's something to know is that the shaped value function, this value function that you learn now with this new reward, doesn't preserve the ordering of states. It'll preserve the ordering of actions in each state. But it will not preserve the ordering of states, which make it not really great for as a heuristic to plan. But fortunately, we can retrieve the original value function by simply adding the potential. And so, in effect, what potential-based reward shaping allows us to do is to learn a correction on top of a domain-independent heuristic that should hopefully be better. And so we use this heuristic in conjunction with the greedy best first search algorithm. And since we care about generalization, we first train on small instances, and also, both for generalization purposes, but also because it's fast and easy. And then we evaluate on unseen and much larger instances. And so for the sake of transparency here, we're going to show you both the best and worst domains that we have out of the 8 that we've tried. And so what we see here is that on the x-axis, we have the number of states evaluated using just the heuristic before learning. In this case, we're showing HAD, but we've tried others in the paper. And then on the y-axis, we compare it to the same problems. For the same problems, how many states were evaluated using the learn heuristic. And so what we see in the blocks domain here on the left is that our learn heuristic improves the search. And in fact, if you look at the right edge of that graph, a lot of domains are not solved just using the heuristic, but are solved using the learn heuristic. In the logistics domain, we do better in some of the problems, but in many of them we do much worse. And so we're not quite sure why this happens. We have suspicions that maybe the training regime that we used was maybe a little too small, but there's something to be investigated further. And so in summary, we use RL to learn a domain-dependent heuristic, and we generalize over problem instances by using neural logic machines. We leverage domain-independent heuristic to accelerate learning using potential-based reward shaping, and potential-based reward shaping allows us to learn corrections to a classical heuristic, enabling us to plan. Altogether, our method is capable of learning goal and problem condition heuristics capable of generalizing to larger instances. Thank you for watching.